Hi guys, and welcome to the third episode in our STEM virtual experiment series. And I'm your presenter, Kemal Rose, and I work as a research officer at the Scientific Research Council. Now today's topic will be phase changes and supercooled liquids. Now there are three fundamental phases of matter: solids, liquids, and gases. Now solids have particles packed closely together and they have a definite shape and volume. Now an example of a solid: a block of ice, a chair, a table. Liquids, the particles are closely packed but are able to flow. They have an indefinite shape, so they take the shape of their container, but they do have a definite volume. An example of that is water. Now gases, their particles are very far apart and they flow freely, and they have an indefinite shape and an indefinite volume. Now what is a phase change? A phase change is said to have occurred when one phase is altered from one form to another. So for example, when ice becomes water, we say that we have a phase change from a solid to a liquid. And when water becomes steam or water vapor, we say that we have a change from a liquid to a gas. Now, what causes phase changes? Phase changes are either caused by a change in temperature or pressure, and we have 6 main phase changes: condensation, evaporation, melting, freezing, sublimation, and deposition. Now, as we can see from our chart, condensation is a change from a gas to a liquid, while evaporation is a change from a liquid to a gas. Melting is a change from a solid to a liquid, and freezing is a change from a liquid to a solid. Sublimation is a change from a solid to a gas without going through the liquid phase, while deposition is a change from a gas to a solid without going through the liquid phase. So what is a cooling curve? A cooling curve is a line graph that represents the change of phase of matter, typically from a gas to a solid or from a liquid to a solid. And the independent variable is time and the dependent variable is temperature. So a cooling curve can be used to investigate the change of state by measuring the temperature as the substance cools. So the temperature stays the same at that point where the state changes either from gas to liquid or from liquid to gas. And from this we can get either the condensation point or the freezing point. Here we have a typical example of a cooling curve. On the x-axis we have the time, and on our y-axis we have temperature. Now as the gas cools, we come down to a point where the temperature remains constant as it changes from a gas to a liquid. Here we have our condensation point. And then as the liquid further cools, we come to a point where the temperature remains constant again and it moves from a liquid to a solid. This is known as the freezing point, and then the temperature further decreases as we have our solid. Now we look at supercooled liquids. Now what is supercooling? Supercooling is a process of lowering the temperature of a liquid or a gas below its freezing point without it becoming a solid. So it achieves this in the absence of a seed crystal or nucleus around which the crystal structure can form. But note, once these are triggered, the supercooled liquids can solidify or crystallize, releasing large amounts of heat, and this gives us an exothermic reaction. So an example of this is hot ice, i.e. sodium acetate, which is used to make hand warmers. Now let's do an experiment. We just spoke about supercooled liquids, so now we are going to make one. We are going to make sodium acetate. Now what you will need is some vinegar, baking soda, a pot, a glass measuring cup, please ensure that it is heat safe, a dish, and a spoon. So let's remember, this is an exothermic reaction, which is a reaction that releases heat, and that's why it's called hot ice. And now we're in the lab to do our experiment to make our hot ice. For this experiment, you will need baking soda, white vinegar, a dish, a pot, a stirring rod, a tablespoon, and something to measure your vinegar in. Alright, so now we measure our vinegar about 1 liter. Measure 4 tablespoons of baking soda and add it to our vinegar. Ensure to add the baking soda slowly, or what you will get is a vinegar baking soda volcano which will overflow your container. So as we're seeing the fizzing, this is caused by the reaction. Vinegar is acetic acid and baking soda is sodium bicarbonate. Together, when they're added together, we get sodium acetate, carbon dioxide, and water in excess. So the fizzing that we're seeing is the carbon dioxide being released. Okay, so now we will place our pot on a hot plate or stove at medium to low heat. And this is in order to get rid of the excess water molecules, because sodium acetate in this state is useless. We need to get it a bit more concentrated so that we can make our hot ice. If you do it at high heat, don't worry, you might see a yellow to brownish discoloration, but the experiment will still work. We boil the solution for about an hour, but for the most efficient results, what we want to see is a crystal layer or film on the top of the surface of the solution. Then we pour out our solution into some heat-resistant glassware. Afterwards, we put our solution into an ice bath or the refrigerator to cool for about an hour. Now, to kickstart the process, we can use some of the seed crystals that we would have gotten from the boiling of the solution. That's that thin film that we would have seen. Those are the crystals which we can use as a trigger to start our reaction. Now it can work without it, but in case you try it and you're seeing nothing, just add a few crystals and they'll work like magic. So now we have our sodium acetate solution, which as a super cool liquid has reached its freezing point, but it is still a liquid, it has not become a solid. But once triggered, whether it's by a seed crystal which we're going to use or a touch of a finger, any little bump will cause your solution to solidify or crystallize. Now for the fun stuff. Here we have our hot ice sculpture, or liquid becoming a solid. If we touch our ice, we'll realize that it is hot to the touch. This is as a result of the exothermic reaction in which heat was released in the formation of our structure. One more thing, guys, remember, in case you accidentally bump or touch your sodium acetate solution and it begins to solidify before time, you can always remelt it and redo the experiment. Thanks, guys, for joining us in our third and final episode of our STEM virtual experiment series. and we hope you had fun making hot ice at home.